for the introduction. So my name is Wei-Che Tai from Michigan State University. And let me start my presentation. So before I start the technical content, I would like to give a brief introduction about Michigan State University. So Michigan State University is a state-funded, then-granted university. We resided the state of Michigan in the city of Lansing, the state of Michigan. So it's state of Michigan is in the Midwest part of the United States, very near to Toronto, Canada. And here shows an aerial view of our campus, and here is the building of our department, and this is the picture of our department. We have about 40 faculty members and over 1,000 students. And across of our building is the American Football Stadium. So Michigan State University is very famous for its sport and student athlete activities. And here shows the picture of the football stadium, and this is very common during a football game. The stadium can accommodate like 70,000 to 80,000 people, and it's always full-seated during the football season. And our football team, American football team, is very strong. We planned the 6th national championship so far. So I hope you have the chance to visit Michigan University and for our beautiful campus. And next, let me start today's presentation. First of all, I would like to give a brief outline of what I'm going to talk about today. First will be the motivation of the study, and include a brief introduction of the inerter dampers, and with some application of the inerter damper to large-scale energy harvesting. Next, I'm going to talk about the limitation of the current state-of-art inerter dampers. And then I will introduce some nice work have been done that use nonlinear vibration harvester to overcome the limitation. And followed by the proposed inerter-pendulum vibration absorber by our lab. And we did several comprehensive theoretical studies, including the harmonic excitation and the random excitation. I will show you some results for this study, and this talk will be concluded with conclusion. So first of all, let's look at what exactly is the inerter damper. So inerter damper is a relatively new vibration suppression concept that was introduced about 20 years ago. So it's considered as a third passive control element in addition to spring and viscous damper. So as we know, spring will provide a restoring force proportional to the relative displacement, and viscous damper provide a damping force proportional to the relative velocity. And then inerter will be a concept that provides a resistant force or inertial force proportional to the relative acceleration between its two terminals. So it can be considered as a third element, a third passive vibration control element. And then in the literature, inerter dampers there are two popular ways to realize the inerter damper. First one is by ball screw mechanism, and the second one is by Rankinian mechanism. So here shows two prototypes. And for these two mechanisms, their function will just be translate linear vibration into rotation of an object with heavy or larger mobile inertia. And for example, here this ball screw mechanism, you can see as the the screw moving back and forth, the screw will drive the knot, and this knot is the flywheel is attached to this knot, and the linear motion will be converted to rotational motion of the flywheel. And by using the moment inertial flywheel, this kind of a device can typically generate very, very large inertial force using relatively light physical mass. So, for example, in the literature, it has been reported that the 1 kilogram flywheel can provide about 60 to 200 kilogram equivalent mass. And this equivalent mass is also known as inertance in the literature. So this device provides some opportunity with a compact design, but provide a large force, so that it's very popular when applying to vibration suppression for large-scale structures like buildings or cars. And next, I'm showing some application of the inerter damper with energy harvesting. So it turned out that the inerter is also popular for large-scale energy harvesting. The reason is as follows. So vibration in large-scale structures such as buildings or cars typically will have a low frequency and a large amplitude. So for example, the dominant vibration frequency in a vehicle's suspension is smaller than 10 Hertz. Then large amplitude and low frequency will give a hard time to energy harvesting because the efficiency will be very low. Imagine that we just use a generator, like electro generator, try to convert this vibration into electricity, and the efficiency of the generator typically is proportional to its rotational speed. So if the frequency is low, the vibration frequency is low, then the velocities will be low. So to increase the efficiency of energy harvesting, people just a lot of researchers just use the inerter to combine it with electromagnetic generator. And here's a both screw example, and here's a rack and pinion example. So for both examples, the both screw mechanism or rack and pinion mechanism, or their function will just be convert low-speed linear vibration to high-speed rotational vibration, so that the energy harvesting efficiency can be larger. So that's why it's popular in large-scale energy harvesting. And here are some typical examples. So inerters damper have been used to suppress vibration for buildings. Here is an example of a 3-story building subject to ground motion. And also it has been widely applied to in vehicle suspension to harvester, to replace the traditional viscous shock absorber to energy harvesting shock absorber, so that the people can harvest energy from vehicle's vibration. However, there is no free lunch. Inerter damper, even though it has been applied to energy harvesting the vibration suppression, it turned out it's very hard to achieve these two objectives at the same time. This is because the majority of inerter dampers are based on the linear design, or they operate based on the basic principle of linear resonance. To demonstrate this, some researchers have already demonstrated this. So here shows a theoretical study where the researchers intended to combine a two-mass damper with inerter damper. So inerter damper is connected between the moving ground and the two-mass damper. And on the other hand, the two-mass damper is connected to the main structure with an linear electromagnetic transducer, so that the relative vibration between the two-mass damper, and the structure will be converted into electricity. And on the right column shows the predicted power and predicted vibration of the structure. So as you can see, this is a linear system. So as expected, the power will reach its maximum when drive at the resonance frequency. And this is the biggest drawback of the linear system. It's a power generation that relies on linear resonance. As a result, at the power that's maximum, the vibration of the structure will also be maximum. And furthermore, when power increase, the vibration will also increase. They just share the same trend. So in conclusion, in short, there always exists a trade-off between between vibration suppression and the energy harvesting. Then a question then arises: how can we achieve these two objectives, these seemingly conflicting objectives at the same time? So to this end, okay, I think I have some connection issue. Let me. Oh, okay, here we go. Sorry, my internet was slowed down a little bit. All right, so to achieve the two objectives, several researchers have turned their attention to nonlinear absorbers. So here shows two examples of nonlinear absorbers. In particular, these absorbers are known as auto-parametric vibration absorbers. So this picture shows a pendulum vibration absorber. So inside this pendulum, there is three permanent magnets, and these two are fixed, and the middle one can free to move. So when the structure is vibrating, this structure when subject to force and vibrating up and down, the pendulum will absorb its vibration and start to swing when certain conditions are met. And when the pendulum is oscillating, the internal magnet will oscillate back and forth and to generate the electricity. And this kind of device is known as auto-parametric resonance because the pendulum is excited by parametric excitation, or more precisely by 1 to 2 internal resonance. When these conditions met, or in other words, when 1 to 2 internal resonance occurs, interesting phenomena will show up. So here at the bottom are the experiments results of this device. First shows the vibration of the structure. Second shows the harvested energy. So as you can see, within certain frequency range, the vibration will decrease simultaneously, or at the same time, the harvested current can increase. In other words, something interesting happened. The vibration energy being transferred to the absorber and without coming back. And then this phenomena will be beneficial to achieve the two objectives at the same time. On the other hand, on the right column shows another example of auto-parametric resonator. So here's a cantilever beam with a piezoelectric element attached. And the bottom is the primary structure and isolated with some spring. And this is the moving ground. So when the structure moving up and down, and when auto-parametric resonance conditions are met, this cantilever beam will oscillate back sideways. And also, this is also considered as one example of auto-parametric resonators. And it also shows simultaneous vibration suppression and energy harvesting. So, inspired by success of the nonlinear vibration absorbers and the advantage of inerter dampers, in our lab we propose new type of vibration absorber that integrated the inerter damper and the pendulum vibration absorber. So here shows the design drawing of the vibration absorber. It consists of a recompendium inerter and the pendulum vibration absorber and the generator. So the recompendium mechanism will convert the structure vibration into rotation of the carrier, this disk carrier. So when the recompendium moving back and forth, the carrier will rotate with angle theta. And this generator is connected to the pendulum with a set of bevel gear, so that the pendulum's oscillation will drive the rotor of the generator. On the other end, the housing of the generator is connected to the carrier with another set of bevel gears. And consequently, the rotation of the carrier will drive the housing of the generator. And then the relative rotation between the rotor and the housing will generate electricity due to Faraday law. Then this device can be used to suppress vibration and harvest energy at the same time. To examine its effectiveness, we conducted a series of theoretic study. We apply this device to a single degree of freedom spring mass damper structure, and this structure is subject to external force. And next, I'm going to show you the study. We consider the two type of forces. First one is a harmonic force, single harmonic force. Second one is a random excitation. Then I will show you next I'm going to show you the theoretical result. First of all, let's look at the equation of motion of the system. So the equation of motion of the system is governed by two parameters. First one is the angle theta. That's represent the structure's vibration. And the second one is the pendulum motion. And for simplicity, we assume the energy harvesting circuit to be just a simple electrical viscous damper, and represented by this parameter E. So here are the four parameters that govern the equations. The first one is mu r, molar inertia of the pendulum. Second one is eta, represent the pendulum length. And the third and fourth one are damping ratio, viscous damping ratio. To get a better idea of the behavior of the system, we did some simple asymptotic analysis. So it turned out that depending on the vibration motion, the pendulum will oscillate at a steady state, oscillate with respect to an equilibrium, dynamic equilibrium position called phi 0. So depending on the value of phi 0, the system will possess different nonlinearity. So if we assume, for example, one typical example would be phi 0 close to pi over 2. So if we assume phi 0 equal to pi over 2 and expand the equation of motion in terms of asymptotic series with small parameter epsilon, we will obtain the following equation of motions. And the most important part of this will be these nonlinear terms. These nonlinear terms are quadratic terms, and they arise due to the inertia effect. For example, this is from the Coriolis effect, this is from the centrifugal effect, and these two are from the Euler force effect. And another important feature will be the pendulum's motion. The pendulum's motion is governed, is driven completely by pure nonlinear term from the theta's motion or structure's motion. As a result, we call this nonlinear turn as essential inertial nonlinearity. And because these turns are quadratic turns, we expect that they will give rise to, or they will lead to 1 to 2 internal resonance. To see that okay, all right, and then next we consider a second case. This case will be when the pendulum motion mainly oscillate with respect to phi 0 equal to 0, so the original equilibrium position. This typically occurs when random vibration is considered. And when in this scenario, the nonlinearity term are no longer quadratic, they become cubic. So the behavior of the system will change. This will be also demonstrated later. So first of all, let's consider harmonic excitation. So here shows the study for harmonic excitation. For harmonic excitation, we are interested in its resonance behavior. To predict the resonance response, we use the harmonic balance method and combine with the method of multiple scales in order to determine its resonance components. So the system can be governed by primary resonance or can be governed by 1 to 2 internal resonance. And these two response resonance regimes are separated by a bifurcation boundary. And this bifurcation boundary is a periodic doubling bifurcation boundary. And if we keep increasing force, well, the system will encounter another periodic doubling bifurcation and then quickly enter quasi-periodic regime or chaotic regime. So our interest will be within this regime because we know that this regime will be beneficial for vibration suppression energy harvesting. So to demonstrate the behavior, the distinctive behavior of the system within these two regimes, we plot the time series of the system at 2 points, point A and point B. So point A is in the primary resonance regime, and you can see the pendulum's motion is governed by primary resonance, or we can see it from it's a fast Fourier transform. It's governed by primary resonance. The harmonic number is 1. That means the oscillation frequency is equal to the excitation frequency. Another feature is this: the pendulum motion will oscillate with respect to a non-zero dynamic equilibrium point. This is due to the centrifugal effect. On the other hand, if we slightly increase the force a little bit so that the system arrives at the point B, the dynamic behavior would drastically change. So the pendulum motion will have a much richer harmonic components. And its FFT demonstrate that in addition to primary resonance, there will be very strong subharmonic, 1 to 2 subharmonic resonance show up. And this is due to the system just undergo periodic doubling bifurcation. Okay, now these figures clearly demonstrate the parameter space, the required force, and the excitation frequency for system to have 1 to 2 resonance. And the next question will be, how can this 1 to 2 internal resonance help us? So to answer this question, next we consider some parameter studies. So we particularly interested in 2 parameters. The first is the moment inertia of the pendulum, and second is the pendulum length. So the first figure shows how the bifurcation boundaries change if we increase the moment inertia from 0.2 to 0.3. And you can see the bifurcation boundary shift to the lower frequency regime, and the required force will be lower as well. And more importantly, the bifurcation boundary will become wider. That means we have larger parameter space for 1 to 2 resonance to occur. This will be beneficial to the system. On the other hand, lowering the pendulum length will have a similar effect, not a similar effect. Lowering the pendulum will also widen the 1 to 2 internal resonance regime. This can be clearly seen here. So the dashed line shows the bifurcation boundaries for eta equal to 0.6. And the solid line shows for the case eta equal to 0.3. And then for the shorter pendulum, you can see the bifurcation boundary is clearly wider. That means it's also good for internal resonance to occur. And next, I'm going to demonstrate how this internal resonance will help the vibration suppression and the energy harvesting. So for a fair conversion, we consider linear benchmark or a linear counterpart of the device. This device is obtained by lock the pendulum at a fixed angle. So for the linear system, the pendulum no longer oscillates. So it's just equal to a traditional Recompinian type of inerter damper. Then we compare its performance with a free pendulum or the nonlinear absorber. And we consider a particular force equal to 0.017. And for this force, the nonlinear system will have internal resonance for a certain frequency range. And we consider two mass moment inertia ratio, small moment inertia and a large moment inertia. And for fair comparison, we adjust the parameters, the damping, electrical damping of the linear system and nonlinear system, such that in a way that their maximum power are the same. So if their maximum power are the same, the system that can achieve this with smaller structural vibration will be a better device. Then here's the result. The solid line, the red line shows the nonlinear response, and the black line shows the linear one. And the dashed line is for smaller mu r, and the solid line for larger mu r. When all these four cases have maximum power, their structures vibration are different. First of all, let's look at the dashed line, smaller mu r case. You can see the maximum structure vibration is pretty much the same. And the inerter damper actually perform worse. The nonlinear damper actually perform worse for certain frequency range. But on the other hand, if we increase the moment inertia ratio, then the nonlinear system starting to become better. Especially within these bifurcation points, the structure's vibration significantly reduce. And this is achieved when both systems have the same power. It means something must happen. Some energy has been transferred to the vibration absorber from the structure. To see this, we consider the time domain response of the nonlinear system. Particularly, we pick the excitation frequency at the maximum structure vibration. And the left column shows the pendulum motion. You can see the pendulum motion have very rich subharmonic components. And these subharmonic components can, because the can have the pendulum oscillate more vigorously, then the pendulum motion can be converted into electricity by the generator. On the other hand, the structure's motion, surprisingly, is still dominated primarily by the primary resonance. And the subharmonic resonance components are relatively small. It's about 10 times smaller, more than 10 times smaller than the primary resonance behavior. In other words, this subharmonic, this internal resonance behavior is only obvious on the absorber or the pendulum, and it's not showing up in the structure. So that's the reason why the pendulum can absorber can generate more electricity without increasing the structure's vibration. So the conclusion will be the pendulum absorber possesses much larger subharmonic resonance components, and these are beneficial for energy harvesting and the vibration suppression. And next, let's consider the case for random excitation. So here shows another project in our group. We try to apply this inerter-pendulum vibration absorber to vehicle suspension. So here shows a simple quarter-count model. And this model consists of a sponge mass that represents the car body, and our sponge mass represents the suspension strut mass and the tire mass. And with tire stiffness, and the car is running on some rough ground, and the roughness of the ground is completely random, and it can be considered as Gaussian noise excitation with a specific power spectrum density. And we consider a typical passenger cars and the typical road roughness. This represents average road in the United States by the ISO standard. And then we did a numerical simulation to see how the harvester will perform compared to the linear counterpart. And before I show you the simulation result, I would like to highlight the distinctive behavior of the harvester when subject to random excitation and harmonic excitation. So in harmonic excitation, the pendulum motion will oscillate with respect to dynamic equilibrium position. So you can see this oscillation is asymmetric. It does not relative to phi equals 0. On the other hand, if the excitation is random, the pendulum motion actually oscillates with phi equals 0. This is very different. So as I explained before, then for this kind of behavior, the system will possess the cubic nonlinearity. And this nonlinearity will help vibration suppression energy harvesting as well. So here we show our numerical optimization results where we try to compute the Pareto fronts. So we did two objective optimization. The first objective will be minimize the car body's acceleration so that the ride comfort can be better. Second objective will be maximize dissipated power in the damper so that we have larger potential to harvest energy. And here shows the parental front for the linear case, linear damper. And this trend is by increasing the electrical damping ratio. And here shows the parental front of the nonlinear damper. And you can clearly see the nonlinear damper can achieve better vibration suppression performance with identical harvested power. For example, for these 2 points. These 2 points dissipated around same power, around 70 watts. But the car body acceleration for the nonlinear case is much smaller than the nonlinear case. And this figure just shows the dissipated power in the damper, and we can another important feature, important finding for this figure is that the nonlinear system achieves optimal performance with much smaller damping ratio, and while nonlinear system needs a much larger damping ratio to do this, and this will have a significant effect in terms of energy harvesting. because the electrical efficiency for electromagnetic transducers actually is related to the damping ratio using this formula. And this formula, in this formula, the most important part is the denominator. So the denominator is dominated by the external electrical load and the internal resistance. Due to internal resistance, the electrical efficiency will not be 100. That is, if we input 1 watt of power in the generator, we can only harvest a certain part of this 1 watt of power, depending on how large the resistance is, internal resistance is. Then if the external resistance is very, very small, the efficiency will be very low. But for the damping to be large, the external resistance has to be small. Then we have conflicts. So in other words, the larger electrical damping, the efficiency will be low. Then this will be really bad for a linear system, because previously I showed that the linear system needs a very large damping ratio. So if we consider the electrical efficiency in the optimization, the nonlinear system will outperform the linear system even more. You can see the power for the nonlinear system will drop a little bit. The circles are for the ideal case, and the triangular are the result with electrical efficiency. The nonlinear system drop a little bit because it only needs a very small electrical damping ratio. But for the linear system, the power significant drop because it needs a very large damping ratio to achieve vibration suppression. And then here again, it demonstrates the effectiveness of the nonlinear vibration absorber for random vibration. So finally, here are 3 conclusions, take-home message. First of all, the proposed vibration absorber features nonlinear inertial effects. And these nonlinear effects are beneficial for vibration suppression energy harvesting. For harmonic excitation, you utilize 1 to 2 internal resonance to achieve the 2 objectives. For random excitation, you utilize cubic nonlinearity to achieve a better parental frontier with a higher electrical efficiency. And finally, I would like to thank you all my student researchers, Akash Gupta and Muhammad and Carter Reeves. And also, I would like to thanks to the following funding agency, the Startup Fund provided by Michigan State University, and the discretionary fund provided by the Michigan State Foundation. And here's the end of my presentation, and I'm open to any question. Thank you for your attention.